All right, everyone, welcome. This is it, your final focused review for the Math 219 Midterm 1. We are going to break down exactly what you need to know to walk into that exam feeling confident, and we're going to do it by looking directly at materials from your course and past exams.
Okay, let's just dive right in. Look, this isn't going to be some generic summary of differential equations. Nope. This is a strategic walkthrough of the most important, most common question types that show up again and again and again on this specific midterm. We're building this whole thing straight from past exams, so what you see here today is what you're really likely to see.
So, here's our game plan. First, we'll figure out the patterns of the exam itself. Then, we're going to tackle the two biggest topics, first-order equations and systems. After that, we'll quickly cover the theory questions, for those easy points. And then we'll hit the hard parts and common mistakes, and wrap it all up with a solid strategy for exam day. Let's get into it.
All right, Section 1, the game plan. The real secret to this exam isn't necessarily about having every single theorem memorized perfectly from the textbook. It's about recognizing the recurring patterns in the questions they ask and knowing the procedures to solve them cold. And just look at this, you'll see what I mean. What we have here is question 1 from 2019 on the left and question 1 from 2018 on the right. They look almost identical, don't they? Both of them are first-order differential equations that deal with exactness and integrating factors. The exam almost always leads with this type of problem, so mastering it is absolutely your first priority.
So, let's build our checklist for these first-order problems. When you see one on the exam, the first thing is don't panic. You just need to run through a systematic process to figure out what kind of equation it is and how to solve it.
And this right here, this is the first and most critical question you have to ask yourself anytime you see an equation that looks like m of x comma y dx plus n of x comma y dy equals 0. Is it exact? This one simple question determines the entire path you're about to take.
And this is it. This is the formula you absolutely have to have locked and loaded in your brain. For an equation m dx plus n dy equals 0, you test for exactness by checking if the partial derivative of m with respect to y is equal to the partial of n with respect to x. Get this down cold. It is the key that unlocks the whole problem. And check this out. This solution from the 2019 exam shows it perfectly. The student finds an integrating factor, multiplies the whole equation by it, and then what's the very next step? They check. They check if the partial of their new m with respect to y equals the partial of their new n with respect to x. They have to verify that it's exact before they can move on. This is a non-negotiable step.
So once you've confirmed it's exact, you just follow this 5-step procedure. Step 1, you verify. Step 2, you integrate m with respect to x. And here's the key, you have to remember to add an unknown function of y, we'll call it h of y. Why? Because any function of just y would disappear when you take a partial derivative with respect to x. Step 3 is the really clever part. You differentiate that result with respect to y and set it equal to n. This is what lets you find h prime of y, which you solved for in step 4. And finally, you state your implicit solution f of x comma y equals c. And please, whatever you do, do not forget that constant c.
Okay, but what happens if that test fails? What if those partials are not equal? Well, that's your big flashing sign that the equation isn't exact, at least not yet. Your job is to find a special function, this integrating factor, that's kind of like a magic key. You multiply the entire equation by it to force it to become exact.
And boom, here's a perfect example from the 2018 midterm. The problem straight up tells you it's a non-exact equation. And notice part A, it doesn't just say solve it. It explicitly asks you to find an integrating factor that looks like mu of x equals x to the n. The exam is literally guiding you. It's telling you, hey, this thing isn't exact. Your first job is to fix it.
All right, let's switch gears and tackle the other heavyweight topic on this exam, systems of linear DEs. If first-order equations were the warm-up, this is the main event. Getting these questions right is absolutely crucial. And pretty much all of it comes down to one thing, finding the system's eigenvalues.
Okay, this slide right here, you might want to pause and take a screenshot. Seriously, this is probably the single most important summary for the whole midterm. For any 2x2 system, once you find the eigenvalues of your matrix, you're going to land in one of these 3 buckets. Case 1, real and distinct eigenvalues. That's the nice, straightforward one. Case 2, complex eigenvalues. That's your clue that you'll be dealing with sines and cosines. And case 3, repeated eigenvalues. This is the trickiest one, the one that needs a generalized eigenvector.
Your job is to find the eigenvalues, figure out which case you're in, and then just execute the procedure.
So let's see case 2 in action from the 2018 exam. The eigenvalues here are complex, -1 plus or minus I. Now the key trick here is you only need to find the eigenvector for one of them. Then, using Euler's formula, you expand out that complex solution. Now here's the magic move. You separate that whole thing into its real part and its imaginary part. And because the original DE is linear, both of those parts have to be solutions on their own. And just like that, from one complex eigenvector, you get two real independent solutions. Pretty cool, right?
And now for the trickiest case, repeated eigenvalues. So in this problem, the eigenvalue lambda equals 1 is repeated. When you solve it the usual way, you only get one eigenvector, but you need a second solution. And that's where this generalized eigenvector, eta, comes into play. You find it by solving a slightly different equation. A minus lambda I times eta equals v. You're basically looking for a vector that gets pushed into the direction of your first eigenvector. And you can see the student does that calculation right here. And the final solution needs both the regular and the generalized eigenvector to work.
Okay, let's move on to what I like to call the easy point section. These are the theory questions, and they almost always come down to the existence and uniqueness theorems. If you just know the conditions for the two main theorems, you can answer these questions fast and grab some points.
Now, this slide is all about the key distinction you have to make. There are two different theorems, and you cannot mix them up. For a linear equation, it's pretty simple. You just need to find the interval where the functions p of t and g of t are both continuous. Easy. But for a nonlinear equation, the rules are stricter. Both the function itself and its partial derivative with respect to y have to be continuous in a little box around your initial point. It's a super common mistake to mix these two up, so make sure you know which one to apply and when.
And let's see this in practice. Take a look at the left. From 2018, we've got y prime plus tangent of t times y equals sine of t. That's linear. So the student correctly identifies p of t as tangent of t and finds the largest open interval where it's continuous that also contains the initial point. Now look at the right. From 2016, we have dy over dt equals the square root of y minus 2t plus 1. This is nonlinear, so the student has to check the continuity of both the function and its partial derivative with respect to y to figure out the region where a unique solution is guaranteed. Two different problems, two totally different applications of the theory.
Okay, we're in the home stretch now. This section is all about damage control. We're going to do a final check on the most common, simple mistakes so you can avoid giving away any easy points on the exam.
All right, let's run through these fast. First up, the characteristic polynomial. We've all done it. A tiny sign error in the algebra that makes the entire eigenvalue problem go off the rails. Double check your work. Second, with those complex solutions, it is so easy to mix up the signs or forget which term goes with sine versus cosine. Just be methodical. Third, the integrating factor. You do all that hard work to find it, and then you forget to multiply times every single term in the equation by it. Don't let that be you. And finally, the all-time classic, forgetting the plus c. It is the easiest point to lose, so always, always include your constant of integration.
And honestly, this is something you got to keep in mind. So much of this midterm just comes down to careful, step-by-step execution. You might understand the big ideas perfectly, but if your algebra is sloppy, if you drop a negative sign or mess up a determinant, you're going to lose points. So be methodical, be neat, and be careful. Okay, last section. You've done the review, you know the material. Now let's talk about how to actually perform inside the exam hall, because having a strategy is just as important as knowing the math.
Here it is, a simple three-step strategy. First, scan and prioritize. Do not just blindly start on question 1. Take the first 2 minutes, read everything, and find your confidence builder, the problem you know you can nail. Nailing that first question builds momentum. Second, show your work. This is huge for partial credit. Even if your final number is wrong, if you've clearly written down the correct method, you showed the test for exactness, you wrote the characteristic equation, that proves you know what you're doing and can get you points. And third, if you have any time left at the end, check your answer. Plug your solution back into the original DE. It's really the only way to be 100% sure you got it right.
So I'll leave you with this final thought. When you walk into that exam, have a plan. Know your strengths. Which problem are you going to tackle first to get that first win on the board? Is it going to be the exact equation, the system with the nice real eigenvalues? Decide that now. Go in with a strategy, stay calm, and be methodical. You've put in the work, you've got this. Good luck.